Picture this. You've got two top-of-the-line, insanely expensive network routers, fully wired up, powered on, and they just absolutely refuse to speak to each other. In this explainer, we're going to dive right in and solve a really fascinating networking mystery. We're going to explore the invisible and surprisingly clicky social lives of routers using the OSPF protocol. You know, setting up a network is often thought of as just plugging in some cables and walking away, but the reality? It is way more interesting than that.
I mean, we've all been there, right? You walk up to someone at a party, you introduce yourself, and then you almost immediately realize you have absolutely nothing in common. Or maybe you don't even speak the same language. You just kind of stand there in this awkward, painful silence. Well, surprisingly, this exact same social awkwardness happens inside computer networks too.
You can have this gorgeous physical setup, two incredibly powerful routers plugged into the exact same switch. The cables are totally flawless. The link lights are happily blinking green. They are supposed to be best friends, what OSPF officially calls neighbors. But instead, they end up giving each other the complete silent treatment. The physical connection is right there, but the logical connection is totally dead.
So today in this explainer, we're putting on our detective hats. We're going to figure out exactly why these invisible software relationships sometimes just fail, even when the physical environment is perfectly fine. We really need to understand the psychology, so to speak, of the Open Shortest Path First Protocol, or OSPF. How on earth does it choose its neighbors, and what makes it flat out reject them? Well, it's literally like moving into a new neighborhood. A router's very first step is to walk right up to the proverbial fence and introduce itself. It does this by firing out an OSPF hello message, and it sends this message to a very specific multicast IP address, 224.0.0.5. You can think of that like a neighborhood loudspeaker that only other OSPF routers are tuned into. Inside that hello message, the router is basically shouting out its unique router ID to anyone who might be listening.
But here's the catch. Just hearing a hello isn't nearly enough. Routers are incredibly picky. Just because router A says hello to router B definitely does not mean router B is going to want to share its network secrets. If certain, very strict rules of engagement aren't met during that first handshake, they will stubbornly refuse to become neighbors. So what exactly are they scrutinizing in that hello message?
It's basically a highly strict background check. They absolutely must be on the exact same subnet. Their internal clocks, the hello and dead timers that say how often they talk and how long they wait before assuming you've dropped off the map, those have to match perfectly. They need to belong to the exact same OSPF area, carry unique router IDs so there's no confusion, and, of course, their secret passwords or authentication settings must align. If literally even one of these details is off, deal breaker. The relationship is dead on arrival. Now, when all those rules actually do check out, the relationship moves through a very specific timeline. First is init. Basically, hey, I hear someone. Then, if the rules match, they hit the two-way state. This is a massive milestone. They fully acknowledge each other. From there, they move into the exchange states to swap their link state databases. And finally, they reach the holy grail, the full state, meaning they are completely adjacent and have totally identical blueprints of the network. Okay, but let's pause for a second, because this is where things get really wild. What if we aren't just talking about a cozy setup with two routers? What if you have, say, 20 routers all plugged into the exact same central Ethernet switch? Just imagine 20 people in a small room all trying to swap massive, detailed architectural blueprints with every single other person at the exact same time. It would be pure, unadulterated chaos. The network would literally drown in update traffic. To fix this noisy crowd problem, OSPF has a brilliant trick up its sleeve. On Ethernet links, OSPF completely defaults to a network type called broadcast. And this broadcast type forces the routers to hold a little election. Instead of everyone talking over everyone else, they elect a leader to manage the madness. Enter the neighborhood boss, the designated router, or DR for short. They also elect a backup, the BDR, just in case the main boss goes offline. So instead of everyone forming that heavy, full adjacency with every single person in the room, all the normal routers only form a full relationship with the DR and the BDR. The designated router basically acts like the speaker of the house, efficiently handing out network updates to everyone without the chaotic, overlapping chatter. So in a super dense setup, the routers that didn't win the election, the ones that aren't the boss or the backup, get officially labeled DRO others. And what's super fascinating is how these everyday rank-and-file routers interact with each other. Honestly, it's one of the most misunderstood parts of OSPF. You'd intuitively think that all routers on the same switch eventually reach that full state with each other, right? Actually, scratch that. They don't. DR other routers intentionally freeze their relationship at the two-way state with other non-boss routers. They see each other, they wave, they agree their roles match, but they purposefully refuse to exchange databases directly. Why? To save just massive amounts of network bandwidth and CPU power. It's incredibly efficient.
And this really highlights how OSPF acts kind of like a chameleon, changing depending on where it lives. On one side, we have broadcast networks, like Ethernet LANs, that crowded room that desperately needs a designated speaker. But on the other side, we have point-to-point networks, like dedicated WAN or serial links. This is just a private, direct cable between exactly two routers. Think about it. If you're on a private one-on-one phone call, would you stop the conversation to formally elect a president and a vice president of the phone call? Obviously not. On simple links between just two routers, electing a designated router is completely unnecessary overhead. It actually slows everything down. That's where we come in as network engineers. By going into the router's interface and explicitly configuring the OSPF network type to point, you're essentially whispering to the router, hey, it's literally just you and one other guy on this wire. The routers instantly know to skip the whole tedious boss selection process. They form that fully adjacent relationship way faster, making the entire network far more efficient. Okay, so we've solved the basic communication rules, we've organized the crowds. We're good, right? Well, there is a really sneaky, super frustrating gotcha in the OSPF protocol that can still totally break your network. What if I told you two routers could go through the entire song and dance, become fully adjacent neighbors, and yet still refuse to share their actual routes with each other? Welcome to the mismatch mystery. As a network detective, you'll log into your router, you'll run your commands, and you'll see the neighbor relationship says full. Everything looks totally golden on the surface, but then you check your IPv4 routing table to see the actual paths your data's supposed to take, and the specific routes from that neighbor are completely missing. It's maddening. So what's happening? There are two main silent killers here. The first is an MTU mismatch, where routers disagree on the maximum packet size and just get hopelessly stuck trying to swap databases. But the trickier one is a network type mismatch. If you accidentally configure one side of a cable as broadcast and the other side as point-to-point, they will actually hit that full state. But because their underlying mathematical views of the network are completely out of sync, one is expecting a central boss, the other is expecting a direct line, they'll just stubbornly refuse to use each other's routes. So, wrapping our heads around this, the crucial takeaway is this. Matching your network types on both ends of a cable and really understanding when a designated router is actually needed is the absolute key to solving these weird, silent neighbor mysteries. It's how you keep your traffic flowing smoothly without pulling your hair out. It's pretty mind-blowing when you take a step back. These powerful routers are really just running simple, local, peer-to-peer social rules, saying hello, checking a few parameters, electing a local speaker. Yet that is the true magic of OSPF. It leaves you wondering, just how far can these localized social interactions stretch? How on earth do these exact same rules scale up to route traffic across the massive global enterprise networks that literally power the modern internet? Well, we'll have to save that deep dive for our next explainer. Thanks so much for joining me on this one.